An inertial measurement unit, or IMU, is an electronic device that measures and reports on a craft's velocity, orientation, and gravitational forces, using a combination of accelerometers and gyroscopes, sometimes also magnetometers. IMUs are typically used to maneuver aircraft, including unmanned aerial vehicles, among many others, and spacecraft, including satellites and landers. Recent developments allow for the production of IMU-enabled GPS devices. An IMU allows a GPS receiver to work when GPS signals are unavailable, such as in tunnels, inside buildings, or when electronic interference is present. A wireless IMU is known as a WIMU. The IMU is the main component of inertial navigation systems used in aircraft, spacecraft, watercraft, and guided missiles among others. In this capacity, the data collected from the IMU sensors allows a computer to track a craft's position, using a method known as dead reckoning. Operational principles. An inertial measurement unit works by detecting the current rate of acceleration using one or more accelerometers, and detects changes in rotational attributes like pitch, roll and yaw using one or more gyroscopes. And some also include a magnetometer, mostly to assist calibrate against orientation drift. Inertial navigation systems contain IMUs which have angular and linear accelerometers. Some IMUs include a gyroscopic element. Angular accelerometers measure how the vehicle is rotating in space. Generally, there is at least one sensor for each of the three axes: pitch, yaw and roll. Linear accelerometers measure non-gravitational accelerations of the vehicle. Since it can move in three axes, there is a linear accelerometer for each axis. A computer continually calculates the vehicle's current position. First, for each of the 6 degrees of freedom, it integrates over time the sensed acceleration, together with an estimate of gravity, to calculate the current velocity. Then it integrates the velocity to calculate the current position. Inertial guidance is difficult without computers. The desire to use inertial guidance in the Minuteman missile and Project Apollo drove early attempts to miniaturize computers. Inertial guidance systems are now usually combined with satellite navigation systems through a digital filtering system. The inertial system provides short-term data, while the satellite system corrects accumulated errors of the inertial system. An inertial guidance system that will operate near the surface of the Earth must incorporate Schuller tuning so that its platform will continue pointing towards the center of the Earth as a vehicle moves from place to place. Construction. The term IMU is widely used to refer to a box containing 3 accelerometers and 3 gyroscopes and optionally 3 magnetometers. The accelerometers are placed such that their measuring axes are orthogonal to each other. They measure inertial acceleration, also known as g-forces. 3 gyroscopes are placed in a similar orthogonal pattern, measuring rotational position in reference to an arbitrarily chosen coordinate system. Recently, more and more manufacturers also include 3 magnetometers in IMUs. This allows better performance for dynamic orientation calculation in attitude and heading reference systems which base on IMUs. Uses: IMUs are used in vehicle-installed inertial guidance systems. Today almost every commercial or military water-going vessel has one. Most aircraft are also equipped with IMUs. IMUs are also used alone on air and spacecraft, in order to report inertial measurements to a pilot. They are critical during space missions to maneuver manned or unmanned landers and other craft. IMUs can, besides navigational purposes, serve as orientation sensors in the human field of motion. They are frequently used for sports technology and animation applications. They are a competing technology for use in motion capture technology. An IMU is at the heart of the balancing technology used in the Segway personal transporter. When used in orientation sensors, the term IMU is often used synonymously for attitude and heading reference system. However, an attitude and heading reference system includes an IMU, but additionally, and that is the key difference, a processing system which calculates the relative orientation in space. In navigation, in a navigation system, the data reported by the IMU is fed into a computer, which calculates its current position based on velocity and time. For example, if an IMU installed in an aeroplane were to detect that the craft traveled westward for 1 hour at an average speed of 500 miles per hour, then the guidance computer would deduce that the plane must be 500 miles west of its initial position. If combined with a computerized system of maps, the guidance system could use this method to show a pilot where the plane is located geographically, similar to a GPS navigation system but without the need to communicate with any outside components, such as satellites. This method of navigation is called dead reckoning. One of the earliest units was designed and built by Ford Instrument Company for the USAF to help aircraft navigate in flight without any input from outside the aircraft. Called the ground position indicator, once the pilot entered in the aircraft longitude and latitude at takeoff, the unit would show the pilot the longitude and latitude of the aircraft in relation to the ground. Disadvantages. A major disadvantage of using IMUs for navigation is that they typically suffer from accumulated error, including Abbe error. Because the guidance system is continually adding detected changes to its previously calculated positions, any errors in measurement, however small, are accumulated from point to point. This leads to drift, or an ever-increasing difference between where the system thinks it is located, and the actual location. Because the devices are only able to collect data in a finite time interval, IMUs are always working with averages. So if an accelerometer is able to retrieve the acceleration once per second, the device will have to work as if that had been the acceleration throughout that whole second, although the acceleration could have varied drastically in that time period. Of course, modern devices are able to collect data much faster than once per second, but over time that error increases exponentially. For example, if an individual were blindfolded, moved in a series of directions, and then asked where they think they are, they would only be able to estimate their final position. The more a person were moved while blindfolded, the more inaccurate their guess of where they have ended up. IMUs work in a manner similar to that which human beings use to detect motion, and although they yield considerably more accurate motion sensing than a human being is able to perform, they're still not perfect, and their errors can accumulate in a similar way. IMUs are normally only one component of a navigation system. Other systems are used to correct the inaccuracies that IMUs inevitably suffer, such as GPS, gravity sensors, external speed sensors, a barometric system for altitude correction, and a magnetic compass. TIMU sensors. DARPA's Microsystems Technology Office Department is working on a micro-PNT program to design TIMU chips that does absolute position tracking on a single chip without GPS-aided navigation. Micro-PNT integrates a highly accurate master timing clock integrated into an IMU chip, making it a TIMU chip. So these TIMU chips for micro-PNT have integrated 3-axis gyroscope, 3-axis accelerometer, and 3-axis magnetometer, and together with the integrated highly accurate master timing clock it simultaneously measures the motion tracked and combines that with timing from the synchronized clock, and with sensor fusion it makes a single chip that does absolute position tracking, all without external transmitters/transceivers. See also, attitude control, dead reckoning, fiber optic gyroscope, genesis of the Lytton inertial navigation system, guidance systems, hemispherical resonator gyroscope, inertial navigation system, Kalman filter, LN3 inertial navigation system, MHD sensor, MEMS gyroscope. PIGA accelerometer, rate integrating gyroscope, Schuller tuning, spacecraft, vibrating structure gyroscope, references. External links, description of IMU aiding from roll isolated gyro, inertial navigation, 40 years of evolution, overview at www.WIMU navigation 3-axis IMU, a guide to using IMU in embedded applications.